Okay, so I think I will start. Okay, I mean I will continue. All right. So, all right. So what is this reduction method? Okay. So the method is the following. Namely, you take the condition from right this restriction. Okay. You take one of these restriction conditions. You move it to this optimized expression. All right, that's the idea. Okay, so how do you do this? Okay, so idea is to consider the following Bellman function. Okay, let us take here beta. All right, so that's the idea. Okay, so you see this. Apparently, this here we also have this parameter, extra parameter. All right. So actually, this is. Oh, I find it. Perhaps I will use some other letter. Okay. So actually, what you do, you see, the first step is to transform. All right. This complicated three-dimensional Bellman function into, well, the large family, because this gamma will run over all the positive numbers. Okay, so the large family, but of simpler objects. Okay, and well, what we can hope for, okay, perhaps I will comment on this later. Okay, when we succeed in finding all these Bellman functions, okay, these simpler Bellman functions, then we optimize in a sense. We'll see later. In a sense, we will optimize over gamma. So that's the idea. That's the underlying concept. Okay? All right, and now we'll see how it works here. All right. Okay, so the first comment is that, well, if you consider this inequality, all right, you see this, that's why we struggled for this 0 here. All right? Actually, this thing is homogeneous. No, right? Because when you multiply f and g by some constants, then here this constant does not, this multiplicative constant does not change this event, okay? And here this constant, well, changes this gamma. Okay, so by this homogeneity, you can actually, you can assume it suffices to find this simpler Bellman function for gamma equal to 1. Okay, and all the other Bellman functions corresponding to other gammas will be just some homogeneity arguments, okay, will be obtained by homogeneity arguments. Okay, so we so we take gamma equal to 1, all right, and we study this problem. Okay, so let us. Here, of course, supreme. All right. And now, actually, we proceed exactly in the same manner as previously. All right. Of course, the function will be a little bit different. It's not the blackboard I wanted to erase. Okay. All right. All right, so you see, of course, we have this corresponding v is just the indicator that y is larger than 0 minus x. Okay. Okay, so how do we find this Bellman function?
What modulus?
I'm sorry. Yeah, sure. Thank you very much. Yes. Oh, that would be very interesting. Okay. Yeah. All right. So how do we proceed? All right. So now I will be a little bit quicker. So you see, very similar arguments to the previous ones. Okay, give you that here when y is larger than 0. Okay, then on the set B is just this, okay, let's call this, okay, let it be B0. Then this B0, xy, is just 1 minus x. It's trivial. It's the same argument as previously. Okay, just the constant martingale does the job. All right? Okay. Actually, you know, this equality holds on a larger set. Okay? Remember, here in this two-sided bound, it held outside this square, and here it will hold outside the angle. All right? So actually, on this, you know, on this stripped region, all right, we have this equality. Why is it so? Well, so above the real axis, okay, we already seen why it is so. Okay, what happens here? Then of course, when we start from some point below, okay, it's easy to construct a martingale, all right, which a martingale pair. All right, such that this probability here, this thing, is arbitrarily close to 1, okay, and here the sign of f is not changed. Okay, that's simple. You just take a martingale which starts here, it moves, let's say, onto the real axis, or move somewhere to China. Okay, very far. All right, so very far. So this kind of martingale. So if we go very far there, okay, then this probability is as close to 1 as we wish. All right, and on the other hand, this thing is equal to x. Okay, modulus of x, because the martingale f does not change its sign. Okay, so there's a similar argument as previously again. Okay, but a slightly different martingale example, such kind of infinite. All right. Okay. So we have this Bellman function here outside this angle. So here this is y equal minus x. Okay, this is y equal to x. All right. Okay, so how do we proceed here? Well, so again, some probabilistic arguments. Okay. So we want to maximize this expression, right? Okay, so we want to make this probability as big as we can, okay, as large as we can, and we want to, well, keep this first moment small. All right. So well, as we have seen, you know, that the problems here with this martingale, this increase in the first norm occurs when this martingale changes its sign. Okay. So from the point of view of our optimization, okay, it's not efficient, it's not good if this martingale changes its sign, okay, because so in a sense it is also bad if this martingale is close to 0, in a sense, because well, any kind of movement would supposedly would you know, increase this first moment. Okay, that's the intuition, of course. All right. So what would we suspect? Okay, so it's convenient to use this terminology of optimal stopping. It's continuation region and the stopping region. Okay, so so have a look. If we take a point xy here, all right, which does not lie on the y-axis, okay, then look, then such a point does not lie in the stopping region. It lies in the continuation region. There are some non-trivial martingales, okay, or in other words, this Bellman function is strictly larger than v. Why is it so? Because, well, clearly you can construct some martingale pair such that this sign of f is not changed, and g goes to this level 0 with some positive probability, and that gives the increase in v, right? Because, you know, if we just took the constant pair xy, this would be 0, okay, and this would be x, okay. But you know, it's easy. For instance, if you don't know, take a martingale which goes here and here, and then from here it stops, okay, and from here it goes according to the previous rules, all right. So then it goes to 0 with some positive probability, which makes this thing positive, and this thing is not changed. Okay, so we enlarge it slightly. All right. So such points in this angle, all right, are in the continuation region. There are some non-trivial martingales to be considered. Okay. On the other hand, if we are here, if we are on this line, on this y-axis, then well, any movement here, okay, the first move here, the first non-trivial move, it increases f, the first normal of f. So we know if we are really deep down here, right, then perhaps this loss caused by this increase cannot be compensated by the increase of this probability. In other words, it's natural, it's reasonable to assume that this stopping region has the following form, that there is some constant, all right, here, some constant, say alpha, okay, such that on such a half line, okay, on this half line, this B coincides with V, all right, so this belongs to the stopping region, and everywhere else you have the continuation region. Okay, so that's hand waving, but well, that's how it works, at least for me. Okay. All right, and well, and again some examples, experimentation. Okay, a little bit, well, drawing some examples and so on, computing. This argumentation leads to the following conjecture, that that actually for such point xy as here, this is the best martingale pair. This is, if one works a little bit, this becomes very natural. Okay, so everywhere here, okay, we just move along the line of slope 1. Of course, here we move along the line of slope -1. Okay, and of course, here we stop. Okay, and here we go either to the 0, 0 or deep down. All right? Okay, so
So the vertical line, is this also a stopping region? Or, I mean,
not the whole line, not the whole line. Okay, so these examples work for the complement of the square here, right? Okay, so again, this is this boundary case. Okay, so we go here, and so on. Okay, there's question what happens here. That's the only thing which needs to be determined. All right. All right. But it's easy to guess what should be here. Okay, we have already seen what are the extremal examples if you move along the square. All right, and here the situation is the same. Okay, and you just, if you have any point here inside this square, and you just move to the along the line of, say, slope +1. Okay, to the sides of this square, and then move accordingly. Okay. Okay, so if you compute this, where do I have it? Okay, I have it here. Okay. All right. So now, what is the outcome, and how do we compute this alpha here? All right. That's really That's really strange. Okay, I have already prepared the blackboard. Okay, so well, it's very easy now. Okay, because what do we do? Okay, so we already know what happens here on this half line. All right, because here we have that this Bellman function. Well, we expect it, okay, to be minus x. So it's just 0. Okay, this is just b0. Okay, so here this is 0. Okay, we also know what happens here on this line. Okay, so if we compute all these things, okay, so let us write that some examples show that if, okay, say if y is less than x plus alpha, all right, okay, then if you compute what these examples give, then they give that b0 xy, it's equal to, okay, 2x over x minus y minus x. All right, so this is what happens here. This is the formula. Okay, these are just these examples. All right, this is what we get. Okay. And you know, and well, how can we determine this alpha? Well, this is a well-known trick. Namely, you know, we expect Bellman function to be kind of regular. Okay, since it's extrema, so it should have some nice differential properties. And you see, on the other hand, okay, we expect that this inside this square here, okay, we expect that this Bellman function will be also a nice function. Of course, it will be symmetric with respect to the horizontal axis, okay? I mean vertical axis, okay? So in particular, okay, the partial derivative of this Bellman function here inside this square, the partial derivative with respect to x is 0 here, okay? We expect it. Okay, so it should also hold here in this point alpha. Okay, so how do we find this alpha? So this alpha is identified by the condition that this b0, okay, is equal to 0. And if we compute this, we get that alpha is equal to -2. Okay, so this is -2. Okay, and now if we so we have everything. Okay, now because we have this the only thing which needed to be specified was this parameter alpha. Okay, so now we can compute all this Bellman function also inside this square, and what we get, okay.
Sorry. So that y in the equation is alpha, right? You just
I'm sorry. Yeah. Alpha. Yeah. Yes. Right. Yes. Okay. So after all these examples and computations, what we get finally, we get the following formula. All right. Perhaps I will write again some other letter because that's just the candidate. So small b.
I'm sorry, but something wrong is in the region. Y is less than minus modulus of x, or
all right. Okay. Yeah. I mean, and y. Yes. Thank you very much. And y is what's then minus x. Something. Yes. Of course. Thank you very much. Yes. We are inside. Yeah. Yes. Of course. Yes. So finally, if we do all these computations, this is just 1 minus x if x plus y started with 0. Okay, we get Okay, if x plus y is smaller than 0 and minus 2, and finally this formula 2x x minus y minus x, okay, otherwise. All right. So we see so actually this is mostly based on examples. This discovery of this function. Okay. In the notes, I have also wrote some text about an analytic approach to this problem. Okay, but well, due to some time restrictions, I cannot tell about this. But I think that this probabilistic part, it's now it's in a way, perhaps a little new for you. So I think it's more worth to say about this only. Okay, okay. So that was the first part. All right. All right. Okay. Okay. So we have found actually this this two-dimensional Bellman function. Okay. So after this homogeneity argument, we also obtain it with some arbitrary constant. All right. Okay, so perhaps, for the sake of completeness, perhaps I should write here that this function works. Okay, I mean that all these conditions 1, 2, and 3, are satisfied. Okay, and so on and so on and so on. Okay, so this is the function which coincides with this b0. All right. So now, what do we do then? Okay. So now we use this homogeneity property. Okay. So you see, if you have any gamma, for any, perhaps let me, for any gamma larger than 0, then you see that if we write supremum probability minus gamma expectation of Fn Fg all right. So if we write this formula for this modified Bellman function, with this parameter, so what do we do now? Well, some standard arguments. So what we do, we change it slightly. We write it in this way. We can, of course, multiply by this gamma here. Okay, and you see, if the pair Fg belongs to mxy, then the scaled pair belongs to the scaled class. All right. So what you see that actually you obtain that, well, of course, it was just the b gamma 0 xy, and on the other hand, if you look at this formula, this is precisely this our function, let's say b1 0, at the point. All right, so that's the homogeneity argument. All right, so so now we are done with this first part. Okay, we have this whole family of Bellman functions. All right, and now there's this optimization. So how do we proceed? All right, so let us take a look at this problem. Okay, so back to 3 dimensions. Okay, so now there is the second step. All right, so how do we proceed? Well, just write. Okay, at this thing. Okay, so take Fg as in the definition of bx yt, all right? And what do we do? Okay, so we want to optimize this, to maximize this probability. Okay, so what we do? Well, we okay, there's nothing special. Okay, and well, what we know? We know that the first moment, okay, here is bounded by t. Okay, and f is a martingale, so the sequence of expectations is not decreasing. So okay, if we have that this thing is bounded by t, and so is this thing. All right. So that's fine. Okay, we can write that this is smaller or equal. Okay. Let me take a look. Am I writing it the right way?
Maybe we should write gamma.
Yeah, probably. One second. Yeah. Sure. Otherwise, there would be nothing to optimize over, right? Yeah. Sure. Yeah. Okay, so you see we have, all right, let us write it down. Yeah. Okay, and we know that this thing, this thing in the brackets, okay, is bounded by this, all right, let us write it, B10. All right. So actually, you see, we have that this desired Bellman function, okay, is bounded by the infimum over gamma all right. Now we compute this infimum, and that works. That gives the right formula. Okay, perhaps. Well, it's the formula is. It's not complicated. Perhaps it's nice to see what the outcome is. So what you get at the very end, you get that. So we obtain xyt, which is equal to 1 if y plus t is larger than 1, and 1 minus y minus t square divided by 1 minus y square minus x square. All right, otherwise. Okay. Actually, this infimum, all right, is given by this thing. Okay, so perhaps I should write. All right, to be correct. All right, so we obtain this, and actually it can be shown with the use of some examples or something like that. That we actually have equality here, and that's the trick. Yeah.
To go from here to the original function with the 1 in there, because you have jn bigger than or equal to 0, right? You just replace x with x minus 1. Right, so this shift, you're doing the one-sided here, which doesn't have the absolute value on the inside.
Yes.
That allows you, allows for that shift. You couldn't do this.
Yes, in the two-sided case, you have to do something else. Yes. Yes, exactly. Yes, and perhaps I will. Yes, and I will just go to this two-sided case now. Yes. Yeah. Okay. Well, perhaps one comment. I think that this comment is really important. Okay, so you see that the underlying idea of this trick is the following. So actually, you have this three-dimensional Bellman function. Okay, this B0 here. All right. So the point is, you must have some ideas about the extremizers. You must have some candidates for the extremizers. Why? Because when you reduce this problem, you split this problem to the family of simpler functions, you must be sure that in this new setting, this easier setting, these optimizers will also be inside, right? That they will be contained in this family of simpler Bellman functions. Okay, you cannot lose these optimizers. Okay, so in a sense, you know, so in a sense, it is efficient, you know, when you pass from this Bellman function, this three-dimensional Bellman function, this family of simpler Bellman functions, it's efficient to take this family large, okay, in order to have plenty of extremizers. Yeah?
So if you just naively take gamma equal to 1 in there, and
Yeah.
effectively you're estimating this difference plus adding a fixed quantity, which is t, that's not...
No, this family, exactly that's the point. This family would be too small. Just this, yes, one element is too small. You have to, you must have this arbitrary gamma here, positive gamma, yeah. Yes, all right. So now we turn to the two-sided case. So I will be brief. Okay, so the same thing, but only here the absolute values exist. All right, so we have fg from m, x, y, all right, and okay. So how do we proceed? We proceed exactly in the same manner. Namely, we consider the following family of Bellman functions, okay, two-dimensional. Let's say, all right, in my notes I have other constant here, okay, perhaps, let's see here, right? Now we have no, unfortunately here, in the two-sided bound, we have, we do not have this homogeneity. All right, condition. You know, we remember this zero helped us because if we multiplied by this gamma, the 0 times gamma was still 0. Okay, here we do not have such thing. All right, so actually we'll have to consider to construct these Bellman functions. Okay, for each c separately. Okay, so here, you know, there are no reduction. We actually have to construct all these functions. Okay, for all c. Okay, not only just one function by some homogenization. All right. Okay. You see, I'm a probabilist. You know, I just erase these boards, you know, randomly. Okay. No. Okay, let us leave this thing. Okay. Okay, so what do we do? So how do we proceed? Okay. All right. So we want to find this Bellman function. Okay. So actually, you know, we have already considered this function, right? We have already, when we started, our first example was about this inequality, actually, right? This is how we constructed this constant c equal to 2, and so on. So we have already studied this function, right? So actually, if one repeats all these arguments from the weak type estimate, okay, one gets that there are two cases. That's kind of strange, but not that strange. So it turns out that for c smaller than 2, the following function works. And actually, that has already appeared here. Okay, we have already proved it. So remember, this function was already on the blackboard, but with C1. Okay, C. Okay. C2, okay, x plus y is larger than 1, okay, and 1 minus Cx otherwise. Alright? It turns out that everything works fine, okay? This formula works fine for C smaller than 2, alright? There is a problem, you know, for C larger than 2, because, you know, this does not work for C larger than 2 because this majorization at the point 0, 0 is violated. Okay? If you just plug 0, 0 here, okay, and C is larger than 2, then you see that this thing is negative. And on the other hand, this function V, right, this function, this here, okay, is 0. Okay, so we do not have this majorization, so something has to be corrected for C larger than 2. Okay. Yeah, sure. Yes, thank you. Yes. Yes. Okay, and now, you know, that's a very nice thing, you know, because that's another general comment. You know, actually, what I mean, if you construct, you know, 10 Bellman functions in this probabilistic setting, you know, the 11th Bellman function is a piece of cake, really. That's how these things work, really. So we'll see that these previous examples give us a complete, you know, a very good intuition about this. Because why? Take a look. This Bellman function for C larger than 2, okay? So this is the two-sided bound, okay? So in a sense, it should be similar, okay? It should be analogous to the symmetrized version of this. Right? So we see, if you look at this picture, okay, and think that we try to symmetrize it. All right? So you see what if you look at this, okay, the following idea comes into your mind. Namely, take a look. We want to symmetrize this thing, right? So what do we do? Have a look. Okay, so again, outside this square, everything is clear. Right here, this is just 1 minus Cx here. All right? But look, this region, or this complement of this square is just the symmetrized version of the complement of this angle here, right? So you see how this splitting, what regions should arise here. Namely, there should be something like this. There should be some constant, say, well, let's say that's alpha minus alpha. Okay, here we should have this square, right? Just the symmetrized version of this square. All right, and now we see, and then we have these examples which moved along these lines of slope 1, right? Okay, so these examples of slope 1 should be here. Okay, so we have these regions here and here. Okay, and we have some additional squares here and here, which will be dealt separately with. All right. And you see, so you see how these examples should look like. It's easy. So here, what do? You just move here or here. Okay. If you are here, then you are done. You will just go here or here. Okay, so this is the example which works for this square. It's exactly as here, exactly, precisely. All right. Here in this region, what do? If you have a point, then you move either to this slide segment and you stop, exactly as here. Okay. or here. Okay, and we know what to do when we are on this line, right? So, and everything is symmetric. Okay, so we move here and here, and so on, so on, so on. And what happens here in this additional square? Well, we already know what is the extremal behavior of the functions, right, of the martingales on squares. It should be something like that. And that's it. That works. That produces the Bellman function.
But how many regions do we have now? I'm sorry.
Okay, so this is. Okay, so this outside of the square is D1. Okay, this is. Okay, I will be consistent with my notes. Okay. All right. I want to be consistent with my notes. So, so this is D2, D3, and D4. All right? And also, this thing is also D2 because it's just symmetric version. This thing is also D3. This is D3. This is D3. All right? All right, so you see this. So actually, you see that there's nothing new here. It's just the symmetrized version of this Bellman function. Okay? And actually, perhaps I will just write the formula for this special BC. All right, so I will keep this picture. Okay, so what you get is 1 minus Cx on D1, okay, y squared minus x squared plus 2x minus Cx. I will specify this number alpha in a minute, okay? But I will just write this formula. xy d2, 2x, 1 plus x minus y. The same formula as previously, minus cx, xy belongs to d3, okay? And quadratic expression, 1 minus modulus of y plus c squared over 4. Y minus 1 square minus x square 4xy belonging to d4. That's the function. What we get after playing with these examples, all right? And this special parameter, right, alpha, is equal to where do I have it? This parameter alpha here is 1 minus 2 over c. All right. So it grows from 0. Okay, when c is equal to 2, then this is precisely 0. It just reduces to a point. Okay, and when c grows to infinity, it just alpha grows to 1. All right. And that's it. All right, and now the passage from this two-dimensional to the three-dimensional setting is the same. It's word by word the same. So I will not write this down. You just write this probability. Okay, you subtract and add the expectation of f. Okay, times constant c, and optimize over c. And that's it. And again, this produces the right Bellman function.
So, no, but there is not a recipe as to how to do this trick, right? That you have to be lucky or insightful enough to keep the optimizers within.
Yes. Yeah. Unfortunately, yeah. Okay, so I think that I will stop here. Right, my time is up.
Excuse me, you mentioned that the iteration technique optimized doesn't work here too. In the last case you considered.
I mean for the c larger than 2. Okay, yeah. Well, this iteration, yes, it works. It works, but in this for instance, for this function, this is unpleasant. This is plenty of calculations, tedious calculations. But yes, it works here. After Something I would have to think. Perhaps three or four iterations, and they do the job. Yes. So this works.
May I ask, do you have any kind of software that gives you affiliation? Because useful tool.
I'm sorry, could you once again?
For example, if you have a problem that can be solved by iteration technique, maybe you are able to produce some software to draw pictures like this, because if you have an
you may try some computer. This can be, this iteration procedure, well, it can be kind of implemented, and that may indicate some perhaps foliation or something like that, perhaps,